For millennia, we've looked up at the stars in wonder, questioning whether we're alone in the vast expanse.
I think exploration is always important. It is important for humankind.
This is really a wild place up here.
Everybody is fascinated about exploration, in particular Mars.
With their eyes set on Earth's cosmic neighbour, scientists are aiming to answer a question that would shake the world.
The early telescopes was showing rivers or canals or channels, which might have also taken water. That's, of course, something absolutely interesting to see. Is there maybe life, even on Mars?
To try to finally find out if there is life on Mars, engineers at the European Space Agency have created a machine like no other. Enter the ExoMars Rover, an interplanetary explorer built to boldly go where no man nor machine has gone before.
This is one of the most incredible engineering projects that's going on in the world right now. There's something very different about engineering something for another planet. It requires a level of thinking, a level of practicality, a level of innovation that you just don't get when you're designing things for Earth.
What we are doing feels like science fiction.
This extraordinary project marks the dawn of a new age of space exploration.
This project will be the culmination of about 15 to 20 years of development. It's a big effort that it cost €1 billion.
It is a wonderful feat of engineering.
An ambitious mission to make the first ever confirmed discovery of life on another planet.
There's no project in the world that compares to this one.
Costing over €1 billion, the European Space Agency's ExoMars Rover weighs in at 310 kilograms. This game-changing robot has 6 sprung alloy wheels designed to compress for maximum traction on the Martian soil, while 3D imaging cameras sit atop a 2-metre-tall mast to survey the landscape. A revolutionary core sampling drill can reach 2 meters below the surface. And a host of onboard instruments will carry out the first ever biological experiments on another planet. This collaborative effort between over 20 countries is overseen by mission manager Pia Mitchdorfer.
Which model did you last use today?
So today we drove around with this one,
Okay.
with ExoTail. I think you know this one already.
Yes, I do. Well, we are waiting for our autonomous navigation to be delivered for ExoMars.
Every component is modeled and tested, but there's one feature that sets this Martian explorer apart from any other.
You see here the heart of it. This is our drill. This is very unique. There is no other rover on Mars that can drill as deep as 2 meters. So this is really special in our ExoMars mission. We expect to find traces of life on Mars, but we have the biggest chance to find any if we go deep in the subsurface of Mars. This is where we expect to find preserved biomarkers or biomaterial, and that's what we are looking for. We are not there yet. Once we arrive and touch down, the real work will begin for ExoMars.
But the team face huge engineering challenges in their mission to land on the surface of another planet.
You have to go from an interplanetary velocity of 10 kilometers per second to a velocity of 0 in a period of about 6 or 7 minutes. If ExoMars crashes, it will be catastrophic.
Where a treacherous alien landscape must be conquered.
One of the real challenges is that the places on Mars that are most scientifically interesting are often the least accessible. If the rover was to get stuck, that would pretty much be the end of the mission.
And ensure that every measure is taken to maximize the chances of finding alien life.
There is no other planet that presents a similar condition in the solar system, and therefore he is the most likely candidate to find some trace of past life.
Searching for life beyond Earth requires engineers to rethink every aspect of interplanetary exploration. This is the European Space Agency's Mars Rover, a mechanized interplanetary ambassador from Earth. By unfolding its 2.3 square metre solar panel rings, this rover draws all the energy it needs from Martian daylight, powering the most complete suite of instruments ever dedicated to searching for life on Mars. But before this robot can roam the red planet, it's got to get there first. At a secure cleanroom facility in southern France, engineers are fine-tuning the spacecraft that will travel to Mars, overseen by Chief Engineer Albert Haldeman.
To get things into space, you need to fight the Earth's gravity. So you need to have a lot of thrust to push against that gravity. One of the Russian contributions to the cooperation is the rockets to launch. And we will use a Proton M to launch the ExoMars 2022 spacecraft composite. The upper stage of the Proton M is capable of accelerating the spacecraft from Earth orbit towards Mars.
The colossal Proton M rocket will launch from Baikonur Cosmodrome in Kazakhstan, the world's largest operational space launch facility. The 4.3-ton missile burns an enormous 2,500 litres of rocket fuel to escape Earth's gravity, and ejects 3 stages to lighten the load. The final stage sends the spacecraft on its 9-month voyage to Mars. But what comes next poses an astronomical hazard.
The most ambitious part is the entry, descent, and landing. Landing on Mars presents a huge challenge because you have to go from an interplanetary velocity of 10 kilometers per second to a velocity of 0 in a period of about 6 or 7 minutes. If ExoMars 2022 crashes, it will be catastrophic.
This spacecraft will be making the 569 million kilometer journey to another world, where an arsenal of onboard instruments will fight their way through the Martian atmosphere.
You need a heat shield to protect that initial ballistic entry and to slow you down. But then you need some other systems to slow yourself further. We have the biggest parachute ever used on Mars. You're going almost as fast on a parachute on Mars as a human skydiver goes with no parachute on Earth. So you need something else to stop you when you get to the ground, and we use rockets for that. We use a controlled rocket thrust to make a soft landing on the surface.
With half of all previous missions to Mars ending in disaster,
failure for ExoMars 2022 is not an option, because this time we really will make it.
But on a mission of this scale, the challenges are relentless.
Landing on Mars is just the beginning. If you land in one place and only have a panorama, it's very limited what you can do and how much you can interact with that environment. The scientific ambition requires mobility.
To find a solution, the team must turn to history's great space exploration pioneers. With the age of rocket propulsion in the 20th century, humankind reached for the stars. In 1957, the Soviet Union launched the very first man-made object into orbit, only to top it by sending a man up there in 1961. But by the end of the decade, the US had managed to land a human being on the moon. The only problem was, if he wanted to explore, he had no way to get around.
Houston, we've got a problem.
At the US Space and Rocket Center in Alabama, aerospace engineer Kimberly Robinson is searching for an interplanetary engineering innovation.
Landing on the surface of the moon for the first time ever was a great accomplishment, probably one of the greatest of human achievements. We soon learned that we were limited by how far the astronauts could explore on the lunar surface. But we understood that if we needed to explore further, we were going to need transportation to help us get to points of interest.
As the first Apollo astronauts realized that moonwalking wasn't going to cut it, engineers Ferenc Pavliks and Sam Romano of the Lunar Roving Task Team stepped in with a solution. This is the Lunar Rover.
This is a replica that was built with some of the original Lunar Rover design team, and I am going to get to drive it, so I am very excited. So let's give it a test drive, shall we? All right, and we're off.
The Lunar Rover marked the beginning of a new chapter of space exploration.
So this was the world's first off-planet, off-road vehicle. It drives like a dream.
Powered by two 36-volt non-rechargeable batteries, and with each wheel having its own dedicated electric motor, the Lunar Rover was a four-wheel drive vehicle designed to enable lunar exploration.
I could only imagine how much fun it must have been on the lunar surface, going through craters, around rocks. It's a marvel of engineering.
Ultra-lightweight components kept the rover's weight down to only 210 kilograms and allowed it to fold, to be stowed for its 240,000-mile journey to the moon.
While the wheels on the replica are rubber wheels, the wheels on the real Lunar Rover were made of a steel wire mesh to get better traction on the surface. A very important feature of the Lunar Rover were these fenders. They kept off the dust from the lunar surface to keep everything working and at the right temperature. And these fender guards here were actually made with the original molds for the Lunar Rover.
A host of onboard equipment, like a reconnaissance camera and a communications antenna, enabled widespread scientific exploration.
It could go about 8 miles per hour generally, but got up to 11.2 miles per hour on Apollo 17. It drives with a joystick. As you can see, my hand, I turn it left or right to go in the direction I want to go. I've always wanted to be an astronaut, but who would have dreamed that I'd get to spend a day driving in a lunar rover? This is pretty incredible for me.
Astronauts on Apollo missions 15, 16, and 17 used this cosmic car to explore further than ever before, expanding the 1-kilometer exploration distance of Apollo 11 to an enormous 31 kilometers on the Apollo 17 mission, allowing astronauts to collect over 5 times the amount of rock samples for examination.
Although the original lunar rovers are left behind on the lunar surface, the legacy of the Lunar Rover is that we still have the engineering technology and know-how to create this wonderful vehicle that we can use as we return the next man and the first woman to the lunar surface in the near future.
In Europe, engineers have adapted the rover concept for the 21st century. But instead of a crude buggy, it's an autonomous, robotic rover that the Apollo engineers could only have dreamed of.
We built the rover to rove in order to expand the access to the Martian surface, in order to find the evidence that it hopes to achieve. Behind me, you have the spacecraft that will go to Mars. And inside it, the lander is actually all folded up in the middle of the descent module.
After a successful touchdown, the landing platform and the rover will unfold, just like the lunar roving vehicle. Once the solar array and mast are deployed, ExoMars is ready to embark on its adventure.
When you can drive on Mars, every day is like a new landing site. You discover through a new panorama of images every day a new place on another planet.
Building on the lunar rover concept, the team have created one of the most advanced machines to ever roam another planet.
We imagine that spacecraft are somehow built by robots and built by other machines because they're so high-tech. But one of the fascinating secrets I find is that spacecraft are the epitome of handmade engineering. All of the structural panels are laid out, the glues are all painted on by artisans, frankly. The technicians and engineers who make these things, they have artistic competence to make perfect assemblies every time. It is a wonderful feat of engineering to see spacecraft come together.
Mars is home to the solar system's deepest canyons and largest volcanoes. But this intimidating landscape is about to be explored by an alien invader. This is the ExoMars Rover, designed to search for extraterrestrial life by reaching places no other Martian explorer has before. Leaving the landing platform behind, the rover will embark on a mission lasting 211 Martian sols, the equivalent of 7 Earth months. Roaming on its non-organic sprung alloy wheels, specifically designed to prevent microbial contamination between planets millions of kilometers apart. And where the distance between worlds is immense, so are the risks. For aerospace engineer Paul Meacham, interplanetary contact is top of the agenda.
The problem with communicating with a spacecraft on Mars is that even travelling at the speed of light, a radio signal will take up to 20 minutes to make the journey from Earth to Mars, and another 20 minutes to come from Mars back to Earth. So if you're trying to drive something by remote control like a rover, 20 minutes later that signal finally makes it to Mars, and of course in which time it's already crashed into whatever the object was. So it's actually downright dangerous. We need to take the time delay from Earth to Mars out of the equation.
To find a solution, Paul must step into another world.
Welcome to Mars.
Hidden away in the UK is a highly detailed 390 square metre facility designed to imitate the Martian surface.
This is our Mars Yard facility here in Stevenage, and it's where we test the future robotic rovers.
This extraterrestrial environment is the perfect place to test and develop ExoMars navigation systems.
This Mars Yard is similar to Mars in a lot of different ways. Firstly, the sand is very similar. We also have representative lighting in here that give us the right light levels that we'll expect to encounter on Mars.
It's also inhabited by its very own resident rover.
This is Bruno. He is one of our earliest prototypes. One of the key features of Bruno is his autonomous navigation system, which is really pivotal for the way the rover will drive across the surface without humans needing to constantly monitor and remote control it. It starts with these two cameras at the top of the mast here, and they see in 3D in much the same way we do. Our brains are extremely good at combining the images from each eye into one consistent flowing 3D image of what's in front of us. Every time the rover stops, it will take a new set of images and it will analyse those to figure out where on the terrain in front of it it can and can't go. So if there's a rock that's too big or a slope that's too steep, it will automatically mark that area as forbidden and it will not go anywhere near it. So you end up with what we call a navigation map.
Using state-of-the-art 3D imaging, ExoMars builds a detailed topographical map. Thinking for itself, it's down to the rover to autonomously navigate a successful path.
We're going to put this autonomous navigation system to the test by using this rock here, but we can put that directly in front of the rover. And what we'll do is we'll give the rover a target the other side of the rock. The rover should identify this as something that is too big, and then we should see the rover taking an alternate path. Here we go. The rover's just effectively determined the height of that rock. And it's determined that height is beyond its locomotion capabilities. So it's immediately turned to the right to drive around that rock such that it doesn't in any way endanger itself. The rover's done that entirely by itself. All I have had to have done as an operator is to give it the target, the end point that I want it to reach. I've told it nothing about the best route to take, or the terrain, or the fact that rock was even there.
But with a goal to explore the most likely hotbeds for alien life, sometimes hazards need to be tackled head-on.
One of the real challenges is that the places on Mars that are most scientifically interesting are often the least accessible. And that means that rather than just going around these rocks, we do need to go through rock fields.
And on the red planet's varied terrain, rocks aren't the only obstacle.
Some of the sand on Mars can have the consistency of talcum powder. So when you drive into that, it's very easy for the rover to dig itself in, and that causes major problems.
In 2009, NASA's Mars rover Spirit became buried in a sand trap. Despite a concerted effort from the team back on Earth, Spirit was unable to move, and NASA's $800 million mission was stopped in its tracks.
Getting out of a situation where the rover has got stuck is absolutely critical. In essence, you have spent many billions of euros and years of development launching this thing to Mars, only for it to get stuck. So that would pretty much be the end of the mission.
When rocks and sand pits must be tackled head-on, the rover team have to look to the innovators of the past. Robotics engineer Kel Guerin is roughing it through the back roads of Ohio.
Oh yeah, this is getting very rough. Oh man, here we go.
In search of a groundbreaking locomotive innovation.
There's some pretty serious dips and sort of rocky areas here. Yeah, this is a four-wheel drive car. It's doing okay over this terrain, but there are places even vehicles like this can't go.
Tackling tricky terrain is a challenge that the US military have faced since the early days of mechanized warfare.
In World War I and II, the military was developing a lot of different vehicles. Most of them had wheels and tracks. There's a lot of areas on the planet that are mountainous or sandy that wheeled vehicles or even tracked vehicles really can't go. It just gets too steep or too rough.
In 1981, engineers Kenneth Waldron, Robert McGee, and Vincent Vonout were contracted by the military to develop a vehicle that could go where no other could.
This tarp is massive. It must be huge.
Their contraption seemed to disappear off the face of the Earth.
Oh my gosh.
But Kel has tracked it down.
All right, let's see how the front of this looks.
This is the ASV.
Oh, it's incredible.
An assisted suspension vehicle that doesn't roll, but walks.
It's like something out of Star Wars.
This extraordinary six-legged beast hasn't seen the light of day for almost 30 years.
When you see it covered, you don't expect it to look like this. You expect it to look like a truck or a car or something like that you've seen before. But it's so otherworldly. It's like a big insect or something. It's hard to describe.
Taking its first steps in 1985, the ASV could stride across 2.5-meter wide ditches and over 2-meter tall walls. This 5-meter long giant weighed in at 2,700 kilograms. with the ability to carry another 220 kilograms of cargo. All thanks to its 6-limbed structure.
Because it was this hexapod design, it had an incredible amount of maneuverability. Each of the legs could move to the side, they could move forward and back. The vehicle could crab walk sideways if it needed to. It can sidestep across a river. Like, that's something that you don't get with any other type of vehicle. It must have been incredible to be in control of this.
This marching monster has long since retired. But to demonstrate the secret behind its locomotion, Kel has scaled it down.
So I wanted to show you how the ASV works, and this little robot that we have here is a perfect analog for that. You see, both the ASV and this robot have 6 legs, so when we command this guy forward, the robot does just fine. It's able to navigate this area really well, and the reason for that is because it has this alternating tripod gait. You see that only 3 of its legs are off the ground at any time, leaving the other 3 to be firmly planted on the ground in a very stable position. And that allows the robot to move with a lot of dexterity and confidence through really rough terrain. We're even getting a little twig in there, and it's just sort of motoring through. It's great.
Moving 2 sets of tripod legs in turn creates the ant-like hexapod locomotion. And upscaling nature's design meant that the ASV could go virtually anywhere.
This is such an unconventional vehicle, and it really shows that it's designed to be as mobile as possible and be able to move over any terrain. At the time, in the 80s, this was considered the world's most advanced walking machine. This was pioneering technology. All of those walking robots that we see now that are going to go and explore other planets and that are able to, because they can walk and because they can navigate over really challenging terrain, it all started here. It all started with this.
For the next generation interplanetary explorer, engineers have equipped the ExoMars Rover with the best of both worlds. Designed to drive across the Martian surface on 6 wheels. But when the going gets tough, it's time to start walking.
What wheel walking allows us to do is to move each wheel or a set of wheels individually whilst keeping the other ones stable. The front wheel and the back wheel on one side and the middle wheel on the other side move forward, and then the reverse will happen, and that sequence will repeat over and over again. This particular wheel walking gait is actually called a tripod gait and is influenced by the way insects walk.
This form of locomotion may not be fast, but by adapting the hexapod walking technology, the team have created a way to traverse the most perilous Martian sand pits.
The normal way of driving the rover, we do expect that to be able to handle 95% of what we encounter on Mars. That 5%, the 5% that can strand the rover and end the mission, that's just too much of a risk to take. Wheel walking is such an incredibly important feature, but this will be actually the first time it's ever been flown on a rover.
And even more world-first systems keep this explorer trekking in the hunt for Martian life.
All 6 wheels are individually controlled, and that allows us to generate different geometries that wouldn't be possible if we had an axle system like a car. So, for example, he can follow a curve, he can crab sideways, and he can even spin on the spot if we need him to, by individually controlling those motors.
By pushing the limit of locomotion, this monumental machine will one day roam Mars without restriction.
When you have a mission like ExoMars that's costing over €1 billion, the benefit of being able to escape from situations that would otherwise strand the rover is so important. In simple terms, we can save the mission when otherwise it would be lost.
With a mission to discover the extraordinary, ExoMars dares to wander where no other rover has before. 4 billion years ago, life on Earth erupted into existence. If our cosmic neighbour also did the same, the ExoMars Rover is sure to find out. On its mission to unveil the secrets of the Red Planet, this hardy robot and its scientific instruments are designed to withstand a bombardment of solar radiation and endure temperature swings from 27 degrees Celsius to a frosty minus 133. But to make the whole mission worthwhile, Rover project manager Bruno Vernay and his team have one last challenge to conquer.
We are in the clean room facility of Thales Alenia Space Turin. This is the clean room where the elements that go on Mars are integrated. This is currently the cleanest facility available in the world for space application.
To eliminate biological contamination on the rover, the team runs tests on an exact replica.
In this area here, we have the ground test model of the rover. There is some activity that cannot be performed on the flight model due to the constraints linked to the cleanliness. It is essential that we have another model where we can try everything in advance of the real operation.
But contamination from Earth is only part of the problem. In 2023, the real Mars rover will touch down on Oxyaplanum, a 212,000 square kilometre plateau tipped as a potential hotbed for Martian life. But in the hunt for answers, searching above ground here will barely scratch the surface. Where the Earth's magnetic field protects us from harmful solar radiation, the dead husk of Mars has no such luxury, and its surface has been under attack for billions of years.
The first 1 meter, 1.5 meters of subsurface has been sterilized by radiation. We think the best opportunity to find organics well preserved is to go in the subsurface up to 2 meter depth.
To find a way to extract pristine rock samples for analysis, could the solution lie deep in the past? Deep below the Cornish countryside in the UK.
Oh, you might want to watch it. It gets quite deep here.
Archaeologist Cassie Newland is heading underground.
It always feels so mysterious. It's like another planet.
She's on the hunt for buried treasure that sparked a mining frenzy.
So this is South Crofty Mine, and South Crofty has been open since medieval times. If you look around the walls, you'll see all the minerals leaching out, and it's those minerals that we're interested in here. They're the reason the mine is here. This is what we're looking for. So if you can see this beautiful stripe running from the top here right down to the bottom, that is a vein that's been exposed in the face here.
The 19th century saw an avalanche of new mineral and ore discoveries. But accessing deep deposits was an enormous task.
So at the beginning in Cornwall, mining is very easy. It's right on the surface, you can see it, it's all sparkly and shiny because the copper is above the tin. You can literally fall over it when you're walking across the moors. But the deeper you get, the more expensive a business it is. At some point, you don't know if it's worth doing all that expensive mining because you don't know how far down that particular vein goes. You need to know what's under the ground before you dig it.
But in 1863, French railway engineer Rodolphe Lecaux invented a clever solution that changed the face of mining forever. This is the diamond core drill. An incredible tool allowing rock samples to be extracted more efficiently than ever before.
This is the core drill. So it's practically the same as that 19th century drill, but just done in modern machinery. And what they're doing here is they're drilling down into the earth to try and discover whether there's enough tin and copper in the Cornish hills to open up Cornish mining again. What makes this such a fascinating innovation is it's like a magical telescope to look beneath the ground. What it does is it sends a hollow drill down into the earth to form a column of rock, and it takes the column out in its entirety. So you can see exactly what is happening every metre under the ground. If you want to know to the nearest centimetre, it can tell you. And here you can see where they're actually drilling. So this is spinning round and round and round. And on the end of it, it's one of these. This is a diamond bit. And this is spinning round and round, and it's biting through the rock and creating a core that's this size.
These drills were the first to produce a core that could be extracted and examined. The key was to keep the sample intact.
So what I'm going to do, some small-scale drilling. Now this is just a regular drill bit. It's a bit of a messy hole and piles of dust on the floor. This is really difficult if you're drilling for something important like an ore. There's very little you can tell about the sawdust. Let me show you that again with the core bit. So you'll notice, totally different drilling experience, very little dirt. And when I take this out, you'll notice I've got perfect cylinder. Absolutely perfect. You can see all the grain of the wood all the way through. There's a complete record of what's inside, and all the information is in here.
Drilling close to the surface is one thing, but exploring at depth requires yet another innovation.
When you're prospecting for ore, you need to drill really deep, like 2.5 kilometres deep. And that poses a lot of challenges. You need to keep that hole open so you can keep bringing those cores up and inspect them and see what you've got. So you do it like this. Put your drill bit on the end, goes in here, and then all of this spins to drill out a core. And as it goes further and further down, the rods disappear into the ground, you add the next one. There we go, connecting up. By the time they finish, they're going to have an unbroken chain of these stretching down thousands of metres.
With this incredible combination of techniques, miners were able to retrieve pristine samples from unprecedented depths.
Okay, this is the moment of truth. Here it comes. So this is our new core. There could be ore in there, could be the secrets of the universe. Perfect. Woo! So now it's time to get the core sample out, and we'll see what we've got. Beautiful. So what you've got here is a beautiful cylinder that is a record of everything the drill has cut through. And when you put them all together, you've basically got a vision of the ground beneath your feet. So this is absolutely essential when prospecting for minerals. So this is still at the cutting edge of mining today. It's pretty ingenious.
Back in Turin's clean room, engineers have created a drilling system worthy of the space age. But before it can extract samples, it needs to reach further down into the subsurface than any rover before.
The drill is able to reach 2 meter depth using 3 extension rods. All the rods are screwed one together with the other by the internal mechanism, such to reach the required length. It's a rather complicated mechanism, and it's rather an achievement.
Mounted on the rover's front panel, a drill box houses the drilling tool as well as 3 additional extension rods. Once the drill box has rotated to the downward drilling position, excavation will commence. And as it descends through the soil, each extension piece will be mechanically screwed to the top, one by one, creating a 2-metre-long chain. Breaking new ground, this drill is able to dig deeper on Mars than any rover before. And once the target depth has been reached, LECO's core sampling technique comes into play.
The drill has not only the capability of drilling, but the capability of acquiring the sample. The drill is coring the sample in the rock, and then when the coring is completed, a shutter is closed, such that the sample can be retrieved.
On its quest, the rover's super tough, diamond-encrusted drill tip will excavate 22 samples before the cutting edge is worn down. Each one will be analysed internally for signs of organic material by an array of high-tech onboard instruments. And the results will be beamed directly to mission control on Earth.
Experiment can be run on Mars without sending sample to Earth. Having the possibility to have a laboratory working for the search of life on an outer planet, that is really incredible.
The ExoMars team have driven drill engineering deeper than ever. They could be the very first to discover something extraordinary.
Nobody has ever attempted to reach the subsurface of Mars in search of life. So in this aspect, our mission is more significant than any other engineering project on Earth.
By daring to innovate and explore further than ever before, the ExoMars Rover is set to change the course of scientific history forever.
To be part of a mission, finding life outside the Earth for the very first time, as a scientist, as an engineer, I think that's a wonderful achievement, and it's been my great privilege to be part of it.
By building on the work of the pioneers of the past, overcoming huge challenges, and pushing the boundaries of innovation.
We can take our curiosity beyond Earth, and that ambition for scientists, for exploration, for human beings, it's exhilarating.
The engineers are succeeding in making the impossible possible.
For me, this mission is so important because it is bringing so much knowledge to humanity. This is incredible.